All right, welcome back. Second half of lecture 36 here. And we're going to move on to the chapter on ethers, talk a little bit, or the section on ethers, and talk a little bit about that. Ethers are generally any compound with a carbon-oxygen-carbon linkage. So COC linkage. We've already seen examples of these, diethyl ether, THF. Diethyl ether is a very common organic solvent. We often just call it ether because it is so commonly used. And then THF is tetrahydrofuran. Which is also a useful solvent in the laboratory. There's a smaller one, smaller cyclic ether known as an epoxide, and that's what I want to talk about because these are very useful compounds. So epoxides are the smallest cyclic ether. Okay, and so three-membered ring with an oxygen and two carbons. Okay, and the reason these are useful is that because of the strain in the three-membered ring, so epoxides themselves aren't typically, our target that we want to make, but they can get us to different places because they are strained and they undergo ring opening reactions quite readily. Okay. And so we'll spend a little bit of time talking about how you synthesize epoxides, and then that will basically be the end of the material for the course here, okay? And so there are two common ways to do this. The first is from what we call a halohydrin, okay? And all right, and so more specifically, a vicinal halohydrin, okay? And so that is going to be any type of molecule where I've got a hydroxy group and a halogen in a 1-2 relationship. They're separated by two carbons, okay? So if I were to number, okay? And so we know how to make these. We said that if we reacted bromine with an alkene in water, we would get opening of the bromonium ion by water. And then we can take these halohydrin products and then convert them to an epoxide. And the way we do that is just by treating with a little bit of base. So Okay, so you can use, for example, sodium hydroxide. We know the pK of water is about 16. The pK of, say, ethanol is around 16 and a half, 17. So it's slightly less acidic, but nonetheless, you'll still get an acid-base reaction where you form a little bit of this alkoxide in solution. And then that species can attack the bromine or the carbon-bromine bond. And it's just like an intermolecular SN2 displacement in the sense that you need to have backside attack of the oxygen. And so we're going to come in from the back and cleave the carbon-bromine bond, kick out Br minus, and that will form our epoxide. Okay, and so let me just emphasize this. Backside attack is required. Okay, it's an SN, it's not an SN2 because it's not bimolecular, but it's a substitution nucleophilic reaction here. Okay, and so we have to get the backside attack. What does that mean? That has important implications for stereochemistry. So as it did for the SN2 reactions that we saw several weeks ago. So okay, so for example, if I come in with a halohydrin like this, okay, a good question, a good exam question is, treat it with base. What does the stereochemistry of the epoxide look like in the product? Okay, and so in order to answer that type of question, you need to arrange the molecule, set it up for this intramolecular displacement. And so for that, we want to have the oxygen anti-periplanar to the carbon-bromine bond. So let me, I'll just redraw it. So we're basically going to put the oxygen up here, leave the bromine in place. And so the right-hand carbon didn't change anything. So it's just put the substituents back in. If I'm moving the oxygen in plane, anti-periplanar to the carbon-bromine bond, I'm basically transposing each substituent by one position. And so my oxygen on the left goes up, the methyl group then comes down and is going back, and the hydrogen is coming forward. Okay. And so this is the conformer that's required for ring closure to make the epoxide in this fashion. So Okay, so we have an anti-periplanar alignment of the carbon-oxygen and the carbon-bromine bonds. Okay, and so when you're facing this type of reaction, you don't want to go any further until you get this conformation clearly drawn on your on your paper, and then you can start to think about the ring closure. Okay, and so if we treat this with base, we'll get to the alkoxide. Okay, and then we need to do the intramolecular displacement. And so the thing to remember here is it's backside attack, and so my oxygen is going to be coming in this way. My carbon bromine bond breaks, and what happens then as a consequence of that is that these substituents on the carbon bearing the leaving group are going to get pushed down. So it's the same. It's very analogous to what we saw in a normal SN2, where we said that those substituents that are attached to the reacting carbon sort of get pushed through that trigonal bipyramidal geometry in the transition state. It's the same thing here. You can't get a perfect trigonal bipyramidal geometry because of you're forming a ring, but it's the same thing where you're basically flopping these through what is a nearly planar carbon center. And so we need to move those substituents down. So let's start drawing the product by drawing what hasn't changed, which is the methyl group and the hydrogen on the left, and then the oxygen, okay? And then I'll put a little arrow here so we know that we made a new bond to this oxygen, okay? And then the question is, where are the substituents? And so the methyl group was wedged and was up, and so it's going to get pushed down as the oxygen closes, but it's going to retain the wedge position, and the hydrogen then retains its hash position and is pushed down. Okay, so the point here is that the stereochemistry of the halohydrin starting material influences the stereochemistry in the product. Okay, so you need to think about the geometry of the halohydrin when you're thinking about which epoxide you want to access. All right, the second important way to make epoxides is by oxidation of alkenes, okay? And we call that an epoxidation reaction. So the general reaction is going to be oxidation of an alkene to make the epoxide with one of these reagents. I just want to say something here also about stereochemistry. So let's just call these R1, R2, R3, and R4. Okay. The direct oxidation of alkenes to make an epoxide occurs in a single step through a single transition state without any intermediates. Okay. And so what that means is that Okay, what that means is that the olefin geometry is faithfully transmitted to the geometry of the epoxide, or the stereochemistry of the epoxide. So the starting material stereochemistry is transferred to the stereochemistry of the product. All right. So if I'm thinking about the substituents here, I can just draw my hashes and wedges and then start to pencil them in. So R1 and R4 are on the same side in the starting material. They end up on the same side in the product, and same scenario for R3 and R2. Okay. So whatever your alkene geometry is, that is the geometry of the resulting epoxide. All right. And so, again, something that you need to think about. All right. So what do we use to oxidize alkenes, or to epoxidize an alkene directly? We use what's known as a peracid. So a carboxylic acid is this type of compound. The per tells me that I've got an extra oxygen, so a peracid is this type of species. Just like peroxide is two oxygens. And so the common peracid that people use is what's known as metachloropurbenzoic acid. And obviously we don't want to say or write that out, so we just call that MCPBA, or some people just call it CPBA, okay? And so what is the mechanism of that oxidation? Let me draw it on the next slide. So the net reaction is you start with an alkene and MCPBA. And you end up with epoxide plus metachlorobenzoic acid. So the oxygen, the extra oxygen in the MCPBA comes directly from the peracid. And so this reaction, it's a little tricky to draw, but as I said, the reaction occurs in a single step. Through a single transition state. Okay, and if I want to draw it, I'm gonna take some room here and just draw it large for y'all. You've got your alkene. And the MCPBA is going to approach. Okay. And what we say happens is that, actually, let me redraw this in a better angle for you. Okay, so I've drawn the MCPBA with a hydrogen bond between the carbonyl oxygen and the terminal OH, and that's okay. And then I've abbreviated the metachlorobenzene group as just AR because it doesn't come into play here. All right. So the arrow pushing for this reaction is a little bit tricky. What we're going to do is start with the alkene pi bond and have that attack the terminal oxygen of the per acid. We then need to break a bond. The weakest bond is going to be the OO bond. And so we're going to take those electrons and push them down over here. And then I can't have 10 electrons around carbon, so I push those electrons over, pick up that terminal hydrogen. Let me just erase these arrows for clarity here. And then take the electrons that were in the OH bond and have them come down and attack the alkene, okay? And so what I end up with then is the product. Plus my benzoic acid, okay? And so it's a tricky mechanism. You should be able to draw it. You know, I think just really, if you spend, 15 minutes with it, you can convince yourself of the flow of electrons. So yeah, we will hold you accountable for this. And the most important point though, is that it goes through a single transition state. And so the stereochemistry in the alkene is faithfully transmitted to the stereochemistry of the epoxide, okay? And so I've given you two ways to make these very important epoxide intermediates. It's useful to do a comparison. Because they can, in some instances, give you different stereochemical outcomes, all right? So if I take cis-2-butene and treat that with MCPBA, we said single transition state, so alkene geometry transmitted to product geometry. So epoxide is up. Methyl groups are on the same side in the starting material. They're on the same side in the epoxide product. And the hydrogens are both going back, okay? But let's think about what happens if you were to go the halohydrin route, okay? So the first step, we'd have to make the halohydrin, so you do bromine and water, okay? And the important point there is that you get you get formation of that bromonium ion, right? And then addition of water to one of those carbons. And so there's an inversion that occurs. And I'm going to skip the proton transfer step because we've now seen this quite a bit, okay? And then we can make the epoxide, so we treat with base. And the key point is that you have to remember, keep that anti-periplanar alignment, so of the CO and the CBr bonds. Okay, and then we do the ring closure, okay? And so what does that give me? It gives me, in this case, the identical epoxide, okay? And it's important to remember that you're going through two inversions in this sequence. And so when you open the bromonium ion, you invert stereochemistry, and then when you displace the bromide, you invert stereochemistry. So both of the stereocenters in the alkene substrate get inverted. In this case, because of the symmetry, we end up with the same compound, but that's not always going to be the case. Okay. All right. That's all that I wanted to say for that. And that concludes the final lecture. Yay. And basically what you guys have left is the final exam. So good luck.